Welcome everyone. So today we are going to discuss on RTL optimizations for power. Okay, so in today's discussion, we primarily talk about what is the basics of power in a digital design and what are the kind of techniques that we should apply just to improve the power efficiency of the design, right? So or you can run the design in low power. Also, one more important aspect of a digital design is clocks, and we most of the time we use multiple clock in our design. In our design needs multiple clock, and that creates certain kind of problems, right. So, we will also discuss about the clock domains in detail. What are the issues with clock domains, and whenever some signal crosses from one domain to another domain, what are the issues may arise and how to tackle those issues, right. So, these are the two things primarily I am going to cover in this module. So, if you just look into the power consumption of a circuit, so in most of the digital design, those are done using CMOS technology. The dynamic power consumption is related to the charging and discharging parasitic capacitance of gates and metal traces, right. And if you just look very high level, that current dissipations which directly related to the power is given by this formula is V into I, the I equal to V into C into F, right, where I is the total current, V is the voltage on which the design is running, C is the capacitance and F is the frequency, clock frequency. So, if you just look into a circuit, usually voltage is fixed, right. So, we do not change much on V voltage, but we will talk about that as well. And the capacitance is related to the number of gates that are toggling at the given time and the length of the routing interconnections. Okay. So, in very basic level or very high level, the capacitance depends on the number of toggling, right. Toggling means when your data state change from 0 to 1 or 1 to 0. So, those are the toggling of your circuits, right. So, whenever you have a lot of togglings, your capacitance will increase and your total power consumption will increase simultaneously, right, in proportionally. So, and the third parameter is the frequency. What is frequency? Frequency is the clock frequency, and it is also directly proportional, the power consumption directly related to the frequency of the clock. So, primarily whatever the technique that we are going to talk about in related to the power optimizations or making the design run on low power is primarily targeting either reducing the capacitance or the frequency of your design. Okay. So, capacitance means number of toggling in your design. Okay. So, these are the two key parameters, and most of the optimization techniques that are applied in digital designs, they play on these two parameters only. Okay. So, let us move on. So, some of the well known techniques that are applied in digital technique, and most well known is clock gating, right. So, what is clock gating? Clock gating is something in your design you try to switch off some portion of the circuit which is not active in a current moment of time, right. So, it is very obvious that if you have a big design, not everything is running in doing the every part of the circuit is doing actual computations in all the clocks, right. In some clock some portion is active, in some clock some other portion is active, and so on. So, the idea is that if you can switch off the part which is inactive or which computed data is kind of unused for a particular clock, then the number of toggling will not happen in that particular circuit, that portion of the circuit, and as a result your power dynamic power consumption of your circuit will reduce, right. So, which is given by this example. Suppose I have this is one circuit, and this is the part of the circuit which is not active in all the clocks, right. So, you can actually apply a clock enable which is when this is 1, then this part is active, whenever that is 0, this part is not active. So, then I can actually gated this is called clock gating, where I am just the system clock or the main clock is gated with this enable signal and get gated with that enable signal and is fed as the clock of this design, right. So, whenever this enable is 0, the clock is something 0. So, that means no change in the data state of this register will happen. As a result, your this circuit will be inactive and there will be no toggling of data. As a result, your power power consumption in this of this part of the circuit will be less, right. So, this is what is called clock gating, and this is very well known technique and is used widely in the specifically in the ASIC targets, not for FPGA, that we will discuss in detail. So, for FPGA this is not a acceptable or that is not a preferable power optimization technique. We should avoid clock gating if you really design something for FPGA. Okay. So, this is one technique that effectively try to reduce the toggling. So, effectively reducing the C, playing with the value C, right, which is capacitance. Let us move on. So, next strategy is something reducing the voltage supply. As I mentioned earlier also that changing the voltage supply is not kind of advisable, it is not a common practice, but what we can do, but this is a very key factor because what we can see that this actually square the total power actually depends on the square of the voltage. So, if your voltage reduced by 2, your power consumption will be improved by 50%, right. So, that is something by 2 it is reduced by 400%, right. So, I mean multiple of 4 times, right, 4 times. So, that is something is going to happen, but this is something is not usually happen. So, we have to make sure that whatever the design you have done, this is actually running by the lowest possible voltage supply, right. So, just to meet the worst case timing. So, you should not run your design in very high voltage even if you are meeting timing quite comfortably, right. So, you should run your design in as low voltage as possible just to meet the worst case timing. So, this is something also an way just to reduce your power of your design, right. So, reducing the voltage supply, but again this is not something is very commonly used. Okay. The third technique we are going to talk about is dual edge triggered flip flops. What is that? So, what we have seen that in the number of the power consumption directly related to the number of toggling of your design, right. So, if you find some high toggling signals, right. So, which actually toggles in every clock, for example, clock, right. So, clock actually toggles in every clock, I mean every cycle, right. So, this is always toggle, this is your clock and it always toggle. So, if you can reduce your frequency, the number of toggle of your clock will be half, right. So, reduce will be also reduced. So, if your current design is running in say 100 megahertz and if you want to make it half, that means now your circuit will run in 50 megahertz. So, number of toggle of clock will be exactly half, right, because now the clock period is double of the previous one. So, your number of toggling of your clock will be half. So, this is something really important, but on the other hand, if your circuit actually meeting timing requirement in 100 megahertz and you make it 50 megahertz, your design will not work, right, because your and if you are running for the same number of same time period, that you will not finish your job, right, because earlier if it needs a 10 cycle, now it will only have 5 cycles. In 5 cycles you cannot execute all 10 operations in 10 cycles, right. So, then what you have to do, you have to use the both rising edge of the clock, right. So, this is your positive edge and this is your negative edge, and you try to use. So, this is one clock period, right. So, this is one clock period and there are 2 edges, right. Usually we all the flip flops are active at the rising edge of the clock. So, whenever there is a rising edge, the data state of the flip flop gets changed. So, if we can use dual edge triggered flip flop, which is what, which actually update on both the clock, this is positive edge, this is negative edge, in both the edges if it toggles, right, data state get changes, then we can actually. So, that means what happened, the 2 operations can be executed within one clock period, right. So, that means you can, even if you make it your clock half, you can effectively execute all of your operations in the specified time period. Right. So, this is the what is use of dual edge triggered flip flop. So, using that we can actually run the whole design using half of the frequency, right. So, if here is an example of a shift register which is actually using a dual edge triggered flip flop. So, what is happening here? So, this is a 2-bit shift register, right. So, there are 2 registers. So, this is data in, this is FF1, FF0, this is FF1, and this is just connected line. So, basically whatever data is coming, it is shifting every clock, right. That is what is the shift register is. But what is happening, this is actually updating in every positive clock passage, but this FF1 is updating either in positive clock as well as the negative clock. So, that means in both the edge of the clock that this data will be updated, right. So, every 2 cycles. So, what is happening here, this F0 is F1 updated by F0, and whatever the content of FF1, that is going with output, right. This is out. So, this is data in. So, this is a shift register where this flip flop is dual edge triggered, and this is just an example. So, dual edge triggered flip flop is something very useful because it actually make your circuit run in half of your frequency, and which is improve your total power consumption of your circuit, right. But one things to be noted here, that not many of the technologies support this dual edge triggered flip flop. So, if it is not supported, you should not use it, right. So, if say if you are targeting some specific architecture of FPGA like say Xilinx Vertex 2 or Vertex 6 or say Altera Stratix 5 something, and that may not have this particular dual edge triggered flip flop. If it is not there, then it has to be implemented using some redundant logic, right. So, some redundant flip flop and gated logic just to eliminate these things, because this is not exactly there, and that actually defeats your purpose. So, your purpose will not be served unless and until that particular device has dual edge triggered flip flop. So, if it is have, we can actually utilize it and we can reduce our power. So, again this is basically technology specific or target architecture specific, but if it is here have, you can actually make your circuits like this. I mean, you can update your registers in both positive edge and negative edge clock, so that this particular flip flop will map to this dual edge triggered flip flop, and effectively your power consumption will be reduced. Okay. So, this is another technique. So, we have learned clock gating, we have learned reducing voltage supply, then we have learned dual edge triggered flip flop concepts. Okay. So, and so now we will move on to the another concept called glitch. So, that also consumes lot of power, right. So, what is glitch? Is basically a hazard or undesired transitions of the circuit, right. So, before the signal settles to a actually intended value. What is that? So, here is an example. So, suppose you have an AND gate where you are actually putting x and x bar. So, the output should be always 0, right. So, it should be always in 0 state, because in x and x bar, if you just do a AND here, it is always 0. But what is happening here, suppose initially my x is 0. So, I have 0 here, I have 0 at this input, and here is 1, because this is negation of this, right. So, I have 1 here. So, because of that output was also 0, right, and now I just move it, make it 1. So, I have now 1. So, similarly immediately this 1 is available here. So, 1 is available here, but since there are some combinational circuit here, it may not come exactly at the same moment, exactly at the same moment here, right. So, that means earlier it was 1, right. So, because it was 0, it is 1 here. So, for a momenter, this is also 1 and this is 1, and the output of this AND gate will be 1, right. This is what is called glitch, but this may be stand for a picosecond or something. But just after the moment this will become 0, whenever this will become 0, this is 1, again this output will become 0, right. So, this is what is called glitch. So, this is just a very simple example just to illustrate what is glitch, but why it is happened. So, if you just think about a circuit, it has multiple input, and this may be have a very long combinational delay, right. So, this is coming from a registers which is coming from a very long combinational delay, and this is very short, right. So, then it is not expected that this both the signal will come at the simultaneously to this input of the registers. So, there may be some delay, mismatch in delay, combinational delay of the inputs. Because of that, this kind of spurious transition will happen at the output, and that is what is called glitch, right. And as I mentioned earlier also, that power consumption it depends on this kind of this toggling. So, that is just going to be very temporarily or momentary toggles, and this glitch actually consumes some power, right. So, and so basic idea is that we try to apply some kind of optimizations or transformation of your circuit, which try to reduce the glitch of your design, right. So, basically if you both the input are kind of balanced, then the chances of glitch is very less, but in reality that may not be always happen, and because of some glitch might happen. So, we try to update or modify my data path or the data path architecture little bit, so that I can reduce this glitch, and which is effectively reduce the power consumption, right. So, based on that there are certain kind of transformation can be applied on RTL circuit just to improve the low power, right. So, for example, choosing alternative data path architecture, restructuring the multiplexer network to eliminate glitchy control signals, then clocking control signals and integrated gated clock. So, these 4 techniques you are going to understand, which effectively try to reduce the glitch of your design, right. So, here is the first example. So, we have an perception that if your number of resources is high, your power consumption will be also high, but that may not be always true, right. So, if you just think about an example here, I have 2 multiplexer here and a adder here, and in another architecture I have 2 adder and 1 multiplexer, but we assume that adder is more complex circuit than multiplexer. So, we can say that this particular circuit has more resource compared to this circuit, right. Now, if you just think about what is happening here, it is this control signal choosing between A and C and B and D here, right. So, when this is 0, I am going to compute A plus B, A will come here, B will come here. So, it will A plus B, output Z equal to A plus B. When this is 1, this C will come here and D will come here. So, it is C plus D. So, either it will computing C plus D or A plus B, and based on this control signal we will decide that output will be either C plus D or A plus B. So, in the alternative architecture, what I have done, I just do operations blindly, right, A plus B here, C plus D here, and based on this control signal I decided to select whether A plus B or C plus B. So, effectively these 2 circuits are same, they are executing the same operations, but their number of resources is different, right. But now assume this particular this control signal is glitchy, right. So, control signal is glitchy means what? So, this is coming from some long combinational input, and that inputs are maybe unbalanced delay, because of there may be lot of glitches happening here, right. So, this might happen to this particular control signal. So, now this control signal is from the control path is moved to the data path. This is your data path, and this is moving through this data path. So, since there are some glitch here, though even though this input are stable, because of there is a glitch here, the output of this multiplexer have some glitch. What does it mean? If it is supposed to select A, but for a moment it will select C. Similarly, it is supposed to select B, it momentarily it will select D, and vice versa. So, there will be glitch at this point, similarly at this point as well, because for a momentary the output will be different, but finally it will be settled down. So, this is what is so that means this control glitch and the control signals move through this propagated through the output and through a long chain, and it will create lot of glitch here, glitch here, glitch here, glitch here, glitch here, right. On the other hand, here this particular glitchy signal is still there, and it only affect the data flow between this. I have only glitch here, I do not have any glitch here, I do not have any glitch here. So, that means I try to redefine my architecture, I try to restructure my data path, so that I can move my control signal as close to the output possible, so that the effect of that glitch in the control signal does not go into more into data path, and as a result the total number of glitch in the resultant circuit will be less, and hence the now total power consumption will also have is less, right. This is just an example. Even based on your design, you might have a different scenario, and you have to consider a different scenario altogether, but this is just to illustrate a fact that sometime even with a more resource you can have achieve less power, right. So, this is one RTL transformation we talked about, which also achieve less power. Okay. So, we will move to the next technique, which is called restructuring the multiplexer network just to eliminate glitchy signal, right. So, as I mentioned in the previous example also, this control signals is glitchy, this CSM is glitchy, because of that it is propagating to the data path and create a lot of glitch in the data path as well. So, what we can do actually, if there are such kind of control signals are there, it might be a situation where we actually possible to remove that particular control signal altogether, and instead of that use some other control signal which is not glitchy at all, right. So, here is an example. Suppose I want to implement a 3:1 multiplexer, right, and I have 3 control signals CS A, B and C. So, this is selecting between A, B, C. I have input A, B, C, I am going to select one of them, and I have 3 control signals CS A, CS B and CS C, which at a time at most one of them will be 1, because I want to select one of them. So, if CS A is 1, I am going to select A, if CS B is 1, I am going to select B, if CS C is 1, that means I am going to select C. So, at most one of them will be 1, that means I am going to select one of them. So, this what is the multiplexing behavior, right. So, now I want to implement this particular circuit using 2:1 multiplexers, right. So, this is one way of doing this. So, suppose I am using CSB to select between A and B. So, if it is 1, B will come here, if it is 0, then A will come here, right. So, it will select between A and B. Now, I can use either C here, right. So, if I use C, I can use A or B, right, CSA or B. If one of them is true, then this data will come here. So, that means A or B will come here, where it is already decided A or B at this point, or if it is 0, that means C will come here, right. So, this is what is the purpose of the circuit, right. So, this is what the implementation is. On the other hand, let us assume that this CSA is a glitchy control signal, right. So, CSA is a glitchy control signal. So, that means it is now propagating through the data path, right. But you can have it another possible, because this I know that CSB and C and A are only at most one of them is 1 at the point. So, I can actually remove this, I can use a CS underscore C to use instead of A, right. So, what I have done here, I use CS underscore C just to select between A and C. If it is 1, then C will come, if it is 0, then A will come. And now, I can use CSB, if it is 1, then B will come, and if it is 0, then either A or C, wherever selected here based on this value will come here. So, still this will do the 3:1 multiplexer behavior, both of them are doing the same thing. The advantage here is there is no CSA, which is a glitchy signal. So, again I am removing a glitchy signal, so that the total toggling of the circuit will be less, and hence I can achieve less power. Again just this is an example, very simple example just to illustrate the fact, but in a real circuit this can be a challenge to identify this glitchy signal and restructuring your multiplexers, right. But this is always possible. This is just a give a pointer that you can actually think about this kind of optimization just to remove your glitchy control signal from your design. Okay. I will move on. So, the next one I will talk about the clocking of control signal, right. So, so far what we have done here, I try to remove this CSA because that is a glitchy signal, but there may be a scenario where you cannot remove, right. For example, here this is a very single mux and this is glitchy, right. You cannot remove it because we need a mux. So, what we can do here? So, what we can do here, I can actually negate the clock and I can make AND gate, and I just AND this CSB, the same control signal with the negation of the clock, and that will actually very helpful just to remove glitches, because what will happen here. So, you try to understand the glitch happen at the start of the clock, right, because whenever the data changes, maybe some data is arrived, some is not arrived. So, there may be some momentary glitch and then it will be settled down. So, whenever you have a use negative edge of the clock, so that means whenever this clock is 1, right, this clock is 1. So, at this moment this will be 0, right. So, this clock bar will be, this is clock bar and this will be 0 and then this is 1, right. This is just opposite of this. So, at this moment, since this is 0, even if there are some glitch here in the CSB, that will not propagate to this signal, right. So, if you just draw it, I just draw it clearly, you can understand that. So, suppose this is my signal and says there is some glitch here. So, this is my CSB, right. So, it is actually 0, but there is a glitch here. So, what will happen, since this is 0, the output would be here. So, it will effectively no glitch at this point, right. So, if this is say this is that signal, right. So, even if there is a glitch, that will not propagate it to this data path. So, I can actually eliminate this kind of glitch using this just clocking the control clock, the negation of the clock, and ending with that clock B and give as a feed at the select line of the mux. So, that this glitch will be eliminated by the negation of the clock, right. So, this is another technique just to remove glitches again, and hence it will also reduce the power of your power consumption of your design, right. So, this is what is another technique. Okay. So, I will move on and talk about the another technique which is called integrated clock gating. So, before that let us introduce the fact. So, what is happening here? So, even gated clock create glitch in the clock signal, right. So, why? Because earlier clock was directly connected to this. So, this is an example of clock gating, right. You can see here this is my clock and this is ANDed with the enable clock. So, this is a gated clock and then this is fed into the clock of the designer. So, this is a clock gating. So, now there may be this enable is maybe glitchy, right, because I do not know this enable may be glitchy and that glitch will propagate to this output of the clock and hence the to the registers, right. So, how we can prevent that? So, you can the example is written here. So, this is my clock and this is my enable. You can see here this is something the glitches, right. So, and this is the actual data 1. So, what is happening here, since this is also the clock is 1 here and this part of the clock is 1. So, there is a glitch will create here. So, for example, here, so this is something this is 0 and there is a glitch. So, it will not be propagated because this is ANDed here, but here what is happening here is this is so this is a signal because this is 1, this is 1, the output will be 1. This is 0, this is 1, but the output will be 0. So, this is the output signal, this is G clock, but here this is 1 and this is also 1. So, there is this momentary glitch. So, which are the redundant things? So, the wanted thing is only this is redundant, this is redundant. So, this glitch will be created in the clock path, right. So, gated clock will create that. So, how to avoid that, right. So, that is avoided by integrated clock gating. What is integrated clock gating? So, let us look into this diagram, it will be clear. So, earlier I use a AND gate just to put and I put clock and enable, right. So, that is what I have done here, right, AND gate, clock and enable. So, what I am doing here, I just put a latch here, okay. I just put a latch here and what I am doing here is enable is the input to this data and this is the enable out, this output is going to this clock and the clock is directly connected to this gated clock, right, and this negation of the clock is giving as the clock to this latch, right, and this is really helpful just to remove this these glitches, because what is happening here, since this is a latch, whenever this is 1, the clock is 1, whatever the data that will update it, when it is 0 it will not change, right. So, this is how it will work. So, suppose this is your clock and this is those glitches are there, and what will happen here. So, since this is clock 1 and this is negation of clock. So, nothing will, so this there is a glitch here, right, you can see here. So, for this part, so this is clock 1, that means clock bar is 0. So, that will not be propagated in the latch out, but this part will be propagated, right. So, this is the latch part, right. So, this will come at the latch out at this point, but at this point clock is 0, right. So, this glitch will not eliminated out at this point. So, what is happening here? So, whatever the glitch is in the negative part of the clock, that will be eliminated by the latch, and whatever the positive part of the clock negative part of the clock will eliminate in the AND gate itself, and whatever in the positive part of the clock, that will be eliminated at the negative using the in the latch, right, because the negation of the clock is using here. I mean, I am just illustrating again, you can understand. So, there is a glitch here which is in spanning over some part of the positive clock and the negative clock, right. So, since this is clock 1, so and this is negation of the clock. So, here clock bar. So, this part of the glitch will not be propagated to the latch out, right, because this will be eliminated by the latch, but this part will not be eliminated by the latch, because at this point latch is 0. So, this will be propagated, but in this that will be eliminated by the AND gate, because at this point clock is low. So, this will not propagated to the actual gated clock, right. So, effectively I am going to get the correct person. So, all these spurious things will be eliminated, right. So, this is what is called integrated clock gating, and what is happening here, I just use a latch at the in the clock, and I just use the negation of the clock at the clock of this latch, and I put the enable through the latch to the AND gate, right. So, through this I can actually eliminate those glitch in the control signal as well, right. And this is also very well used technique for ASIC library, just to eliminate glitch in the control signal. Okay. This is also one of the technique, right. So, so far we have discussed various technique, right. So, what we have discussed? We have discussed about this clock gating, we have discussed about this lowering the voltage, dual edge triggered flip flops. Then I have talked about different kind of optimization technique like RTL optimization technique, restructuring the multiplexer network, or you choose a different architecture, or you clock the control signal, or you do the integrated clock gating. So, these are the all techniques that are we have discussed, and those are actually used to reduce the power consumption of your circuit, right. So, I will now discuss about this clock domains, and then I will again come back to this clock gating, and specifically for FPGA architecture, what is the problem of this clock gating in FPGA architecture and how it is avoided by the FPGA synthesis tools, that at the end of this lecture. But for the time being, we are going to discuss about the clock and different clock domains. When you have multiple clocks, what is the clock domains and what are the issue we will face because of this multiple clocks in a pure design. And remember, clock is very important part of a digital circuit, and whenever you have multiple clocks you are using, you have to be very sincere, very careful in designing your digital circuit. Otherwise, what will happen? Your circuit will become metastable and you have an inconsistent behavior of your circuit, right. So, we will talk about these clocks and clock domains now. So, move on. So, when you are talking about clock, that means clock is something we are driving your digital circuit, right. So, it actually driving all the registers, and most of the register or flip flop is edge triggered. Whenever there is a positive edge, your circuit will toggle, right. Your circuit their state will change, right. Now, we will talk about what is clock skew, right. What are the issues? Because primarily we are going to talk about what are the issues with clock. You should be careful. But the first thing we are going to talk about the clock skew, right. What is clock skew? Is something the same clock is feeding to all the register of your circuit, right. Suppose your circuit has only one clock, not multiple clocks. But our expectation of a synchronous circuit is that that particular clock will reach all the register at the same time, right. If it is happen, there is no problem, but in reality that may not happen, right, because of some delay, as we discussed about this clock gating, or and even the clock path has to be read out through some readout from readout, right. So, that means it may not happen that that all clock actually reach to all the register at the same point of time. There might be some delay, and let us assume a scenario here, and that is what is called clock skew, right. So, whenever it is the difference between that register clock that is achieving arriving to particular flip flop and the difference in time between them, right. So, that is what is called clock skew. And what might happen practically, suppose there are 3 registers in my design, and these 2 clocks are actually coming simultaneously, there is no problem, right. So, there is no problem in here, because I am they are coming in the same time. And but suppose there is a scenario where there is some delay here, and obviously there is some combinational circuit between 2 registers, and this delay of this combinational circuit is DL, and delay of this clock is DC, and DL is less than DC, right. That means the combinational circuit delay of this combinational circuit is less than of the delay in the clock path. That means what? This data arrive early, then this clock arrives, right. So, that is something is the problem, and that is very serious issues, because what will happen because of that, the same signal could propagated through the stage 2 and stage 3 at the same edge of the clock, which is very serious issue and have a catastrophic failure of the circuit, right. Well, I will explain that what is happening here. Suppose whatever the clock is coming here. So, suppose I am talking about the clock 2, right. So, clock 2. So, usually what will happen in clock 2, whatever the data here, that will come here, and whatever the data of this register, that will go out, right, in clock 2. In clock 3, whatever the data of this, it will come out here, and whatever the data that of this clock 2, that is fed here, and that will come out of this register now, right. So, that means whatever the data is coming at input, and after 1 latency, 2 latency and 3 latency will go to the output, right. So, that means the same data is not. So, if you have one data here 1, that will not be propagated here as well as the here, right, because that is something is not allowed. So, whatever the data here, it will come in one in next clock here, then it will come here, right. But because of this problem, this DL less than DC, that may not happen, right. What will happen here? Suppose I am talking about say clock k or clock I. So, the data, whatever data here, it will be available here, and since the data the clock is not still reach here, that clock is coming little bit late. So, this data is already processed and is ready here. So, whenever this clock has come here, the same clock, whatever the clock here, because of that data comes here. So, that particular, so as I was discussing that because of this delay in the clock, whatever the data is processed here, that will arrive at this point, and by the time this clock reach here, that data is ready at the input of this clock, and that will fade out of this register, right. So, this is something, that means the same data whatever is here is ready here, which is something is not expected for digital circuit, and that is something called a serious problem to the circuit, right. So, this is something has to be handled account by the timing analysis, right. So, when you are doing the timing analysis, that has to be taken care. If you have a clock, really have a clock skew, that has to be taken care, otherwise this kind of problem will happen, right. So, this is the problem with clock skew, and that has to be taken, must be taken care during the timing analysis of the design. Okay. So, here is an example that why this is happening here. So, I have 3 set of register F0, F1 and F2, this is F00, this is F1 and F2, and you can see here this clock 1 is ANDed with a clock gate 1, right. So, this is clock gate 1 is a signal which is ANDed here. So, this is FF0, this is your FF0, this is FF1, this is your FF2, and you can see there is no delay here, there is no delay here, but there is a delay here in the clock path. So, this is your clock, it is coming here and it will go through this AND gate and this will reach there, but this data will come immediately here, right. So, that means there is a delay in the clock path and there is no delay in the combinational path. So, there is, that means is actually deflecting this scenario. In this scenario, you might reach to this problem, right. So, this is one issue. We will talk about how to avoid this kind of thing. So, basically just to avoid this, we have to, in the timing analysis, you have to add some kind of constant, so that this clock period is such that this may not happen, right. So, that you can actually avoid this scenario, right. And now we will talk about the clock domains. So, as I mentioned, you might have to use multiple clocks in your design, right. So, clock domain is what? The set of registers, flip flops and this pipeline multiplexers, those are actually driven by a clock, right. So, all the registers of a particular portion of the design driven by a clock. So, that is a domain of this clock, right. So, in this particular scenario, I have 2 clocks, right. So, this domain is driven by this clock 1, this but is driven by the clock 2, right. And so, if you have multiple clocks, it is fine, but the problem is that whenever you are actually passing a data from one domain to another domain, that will create a problem. So, just to specifically say that even the gated clock actually create a different clock domain, right. So, since this is the main clock, it is coming to this particular clock and this is gated here and go as a clock to this, the synthesis tool assume this is a different clock domain, right. So, this is clock domain 1, this is clock domain 2. So, even this gated clock or derived clock will actually create different clock domains, right. So, the problem will happen here in the clock domain is something whenever you are passing a data from one clock domain to another clock domain. So, when you have multiple clock domains, there must be some communication between the clock domain, otherwise you do not need that, right. So, if there are two things are totally independent, there is no problem, but most likely whatever the data is computing here, that is going to be used in the next clock domain, right. So, that is what is happening here. So, this is running in slower clock, this is running in faster clock, and you are doing some operations and updating that, and now what will happen here, right. And this is in this, unless you taken some measures, that will actually create a metastability in your design, right, and which is a serious issue. And the problem with this metastability of this kind of circuit is this kind of failure is not repeatable, right. It may be that if then it is not repeatable in the sense that it may be that if your target technology is, and because this it may varies to technology, right, because it may be happen that in some particular FPGA architecture it is not repeating, I mean it is not happening because of the delay of that particular clock or the devices and some parameters, but in a very faster architecture this might arise, right. And also even when this particular these two clock are really asynchronous, what does it mean asynchronous? They are actually have a different source, right, they are not actually related, this clock 2 are not at all related. So, what is synchronous? Maybe there are two clocks, they are maybe actually generating from the same clock source, and there may be some clock divider or something, and then this is your clock 1. So, this is a divider circuit and this is your clock 2, right. So, that is a source is 1 and you have 2 clocks. So, that is kind of a synchronous clock, though although I mean they have 2 different source, but even specifically if this particular 2, and there are 2 different clock, right, they are 2 asynchronous. This is your clock 1 and this is your clock 2, and this may be say 100 megahertz and this is say 100 megahertz and this is say 33 megahertz. They are not related at all, right. So, they are not, their phase is also not aligned also. Right. So, this kind of in this scenario you never know how exactly they are here they are this rising edge will aligned. So, if they are aligned there is no problem, right. So, this is a faster clock, this may be like this, and maybe some scenario this may align, in some scenario they may not align, some scenario they may not align on something. So, that means they are not repeatable, in some scenario it may occur, some scenario may not occur, right. And the most problem is that this EDA tool does not typically do not detect this kind of problem, right. And effectively they are actually very difficult to detect and debug this kind of clock domain crossing problem, and because of this metastability happening due to clock domain crossing usually do not flagged by the synthesis tool, and even even the simulation tool does not give you any hint. So, and they are not repeatable, they may not happen sometime, and even for technology to technology they may happen or may not happen. So, this is a very serious issues, and this has to be handled with utmost care when you are designing your circuit, right. So, we will talk about that. So, when you are, so there is a very specific example here. So, what is happening and why this metastability happened, right. So, that is a question I am going to ask you, right. The problem is that whenever we know the concept of hold time and setup time, right. So, whenever the basic concept is this, whenever the clock arrives, right, the data must be ready at least before some time, right. So, it must be ready. So, this is your at least sometimes before that clock comes it should be ready, so which is setup time. And similarly, before after the clock at least some time that it should hold there, which is called hold time, so that you have a chance to that register content get updated, right. So, this is called setup time and this is called hold time, right. This is hold and this is set time, and if the data toggles in this period, right. So, this is the boundary, at this boundary even the clock comes at this point. So, this is the point your data state does not change, right. But if your data state changes here, then what will happen? It changes from 0 to 1 or 1 to 0, and that is causing the metastability, and that is happen when you have some data is going from a slower clock to a faster clock, because since they are between this clock their edges are not aligned, their edges are not aligned. So, whatever the data coming here is may not sync with this particular clock, right. Because of that this kind of the problem will happen, and that is actually the problem will happen here is something like that. So, for example, here this is your slow clock, this is your fast clock, you can see. So, this is there is a change, this is the DC delay in that particular clock, this is what I talked about earlier also, and here this is the faster clock is come, and this data is output coming from this. So, this is related to this clock, right. So, whenever this edge come, this data get updated. So, here from here, but it is changing here, right. So, and at this point whenever the data is changing, the clock is also changing, and that is called setup violation, right, because at this point data should not change, because this data is coming from the clock 1 domain which is slower clock, and this data is depend on this clock, and this might change based on this positive edge of this clock, and at that moment maybe the scenario that this clock is also changing. So, that will actually create a hold time violation or setup violation, right, and that is a serious issue, and because of that what will happen, and because of that your data will become metastable, right. So, which is called unstable. So, this is what same example. So, at this point the clock has come and data is changing, and because of that you never know what is that. So, in this state your data neither in 0 state or logic state. In digital I always assume either it is 0 or 1, right, either it is 0 or it is not in between of that, and this is actually 1 means high voltage high, and this is other low, I mean by the setup suspended at a voltage which is not neither 0 or 1, right. So, that is not a expected state, right, and that is called metastability, and that actually this particular metastability will go through this this will go through this circuit following this, right. So, it will actually go through the combinational circuit following this gates also, right. So, this metastability will propagate and may propagate to the output, right. So, because of that this is something. So, high voltage means 1 and low voltage means 0, right. So, it might be some dwelling between the intermediate voltage, and this may reach to some value, I do not know whatever the value will be coming here, some state after some time, right. When the data stable, it will go stable, and that is what is called metastability, and this may carry to the output also, and this is maybe probabilistic. As I mentioned, this whenever I do not know, because this clock is asynchronous, when this will come and this will come, they may not after this they may sync or may not sync, or the data may become metastable or may not, as I mentioned earlier also. So, that is something probabilistic, and this will be fed into logic, and it will be generate output incorrect output. So, this is something metastable signal can be catastrophic functional failure of a design. So, this is something has to be avoided, right, and how we can avoid that. So, there are 3 primary techniques that has to be applied just to avoid this metastability between when your some signal is going from one clock domain to another clock domain, which have a different clock period, right. So, the first technique is phase control. So, that this is applicable when this one particular clock, other particular clock is multiple of one another, right. So, one is 100 megahertz, another is 50 megahertz. Then what we can do, you can use the PLL or DLL, that is phase lock looped or delay lock looped of specifically for FPGA, just to generate the other clock, right. So, here is a slower clock. So, this is a 50 megahertz, and what I am doing here, I just use a DLL to generate the 100 megahertz clock, right. So, this is 100 megahertz clock, and the advantage of having there. So, this actually aligned, because this is just twice of this clock is just twice of this, right. So, ideally all these edges should match, right, and this DLL ensure that it make this clock aligned. So, all these positive edge should be aligned, right? That is what is happening. So, as long as the propagation delay between the flip flop, this slow flip flop to the this propagation delay between the slow flip flop, the first flip flop is less than the clock period of the first clock, right, of the 100 megahertz of this clock, you should not have any problem, right, because these are always aligned. So, the data whatever is generating will be all this data is depend on this particular clock, and since they are always aligned. So, whatever the data change will happen at some point from here, and that will not violate the same setup time or hold time. So, this is what is applicable, this phase control, which is using the phase PLL or DLL when the clocks are multiple of each other. But if your clocks are not multiple of each other and they are completely asynchronous, right. So, they do not have any relation, right. One is 33 megahertz, one is 47 megahertz, one is 11, one is 13, there is no relation. So, in this scenario we cannot apply this phase control technique. What we can do, I can use a double flopping, right. So, the technique is called double flopping. So, again this is that clock 1, this is clock 2, and what I am doing here in the clock 2, I am actually use instead of one clock, I mean one flop, what is happening other scenarios, right. So, this is the normal scenarios, one clock, I am going to use 2 flops in the destination clock domain, right. So, which may be faster or slower. So, the advantage here is that whatever the metastability happen here, it will happen here, and that will not propagate at the output of this register, right. So, what is explained in this register. So, this is your capture clock, that is the clock 2, and there may be some at this whenever this positive signals triggers are there may be changes in data, right, that and that might create some metastability at this point, which is this desync, but that will not propagate it to this register, because this register will be this data will come to this register in the next because this is a faster clock in the next clock, right, and till that point this data gets stable and the output will get stable, right. So, at the output this metastability will not propagate it, right. So, this is something simple or the most convenient or most easy way to avoid this metastability between multiple clock domain, right. So, in theory even you can prove that this metastability may remain indefinitely, or it may occur in this particular even in this scenario, because you might assume that their clock is very fast. So, that whenever this next clock comes, this metastability will come here and that might come here also, right. But in practice that may not happen, right. That may be the scenario in theory, but in practice this is very useful, and we can use this technique just to avoid metastability at the output because of clock domain crossing, right. One point to be noted here, whenever you have this double flopping method, you have to the timing engine should not do any optimization in this technique, because this is a redundant part, and that has to be mentioned, that between the first clock and the second clock domain during this timing synthesis, right. So, sorry, this is first clock. So, this point, right. So, this point, the first clock to second clock domain is ignored during timing synthesis, because that is not required, because that will be taken care of by this technique, right. So, this is that solution 2, and the third solution is the FIFO structure, asynchronous FIFO, which is the conventional first in first out technique, right. It is basically appears everywhere, right. So, whenever you just think about a shopping mall where we that billing point, right, that is we have a queue, right. When that means the speed of the person who do the billing, his speed may be different from the frequency in which the customer comes, right. So, if the customer frequency is high, there will be a long queue. If the frequency of the biller is fast, there will be no queue, right. So, that is something. So, that means the frequency of the biller versus the customer, coming customer, is the two different domain, and their frequency may be different, and we have a queue first in first out, and that is what is this asynchronous queue. That means, if you just reflect the same scenario here, I have this this is the customer side. So, they are writing to this data, and this is the biller side who actually access this data, process the data one by one. So, the way it is happening here is that whatever the data is coming here, they will keep writing in this particular asynchronous FIFO in clock 1, and this will be reading this data in the speed of clock 2, right. And there is no problem, because these two are totally there is no direct communication between these two and these two, right. And what is happening here, but one point has to be taken care, is that what is the FIFO size, because you know that if the speed is very high and reading speed is very low, this will become very long, right. And in hardware you have to fix the size, and it may be that in the scenario that worst case it will cross the size of the FIFO. So, it will overflow, right. So, that means it will create a problem. So, there are two techniques can be done. One is something that if you know the prior knowledge of the transformer, I know that whatever the scenario, the FIFO size should not go beyond 100 or 200, then I can use those that size FIFO just to avoid this overflow, right. Similarly, the other convenient technique is the handshaking, so that when this is full, this process will not write anything, and whenever this is empty, this process will not read anything, right. So, there will be some signal called full and empty. So, when it is full signal coming, this domain from clock 1 will not wait to write unless there is some vacant position available, and similarly, if this empty is 1, that means it is not going to read from this clock 2 domain, will not read anything from this, because there is no data here. So, this is kind of a handshaking through which also this overflow problem can be avoided. So, this is the technique 3. So, as a summary, so this clock domain crossing as a serious issue and create a metastability in your design, and whenever you have a clock domain crossing, you have to use one of these 3 techniques. First technique was that phase control. If the clock is multiple of each other, you should use PLL or DLL of your FPGA just to avoid that, or in general you should use double flopping for the destination clock, so that you can avoid the metastability propagating to the output. And the third technique is more generic or more robust way, is this FIFO. You use a FIFO between 2 different clock domain, and you do this writing completely independent of each other, right. So, this is something, the 3 technique, and these are the issues that will be faced by the multiple clock domain. Okay. Now, I will come back again to this clock gating. So, we have talked about that clock gating is a very useful approach to reduce the power of your design, and now, but the problem of clock gating is that it creates a different clock domain, right, as I discussed earlier also, and that is actually problem for the timing analysis tool and implementation. Specifically for FPGA, in FPGA there we have only one master clock line. So, if you have multiple clock, they will be routed through the normal LART structure, and that will create lot of delay and lot of problem. So, multiple clock domain is not a practice for FPGA target, specifically this gated clock. So, that may not be feasible in a FPGA target, right. So, on the other hand, in ASIC, because they have some flexibility, multiple clock tree circuits are there, and we can actually apply clock gating, but it will come with some problem that we have already discussed earlier, that that has to be taken care, the timing analysis tool has to be taken care of those problem that will come due to clock gating, that has to be there. But for FPGA, this is a big problem, that we cannot use this clock gating I mean at all almost, right. So, that, and you also remember that FPGA is a very power hungry module, which where this power optimization does not work, because it is a redundant technology, right. So, that reroutable interconnections, reprogrammable logic. So, all are kind of a redundant circuits are there. So, this power, this FPGA in general is very power hungry. So, low power technique for FPGA, this kind of thing does not work. So, people who are actually working on FPGA, they do not bother much on this power issues for FPGA target. But on the other hand, in FPGA, this ASIC, they may be very tight requirement of power dissipations, right, and they have to use some kind of clock gating technique just to reduce your power, and also they have some flexibility of clock tree, ASIC clock tree. Using that, you can actually meet your timing, or you can remove the problem that is because of the because of the clock gating. So, for ASIC, this clock gating is very common, and this is not very common for FPGA prototyping. Sorry, for FPGA design. So, whenever you are designing something for ASIC, you might think of having a gated clock in your circuit, but when you are designing something for FPGA, you should avoid use clock gating in your design, right. But now the question is, when you are actually doing the prototyping, ASIC prototyping, what is ASIC prototyping? So, you have a circuit which is actually you have designed for FPGA, and it is a very big circuit. You just think about a processor, which is a very big circuit. Before fabrication, you try to simulate your actual circuit and try to see whether this is working or not, right. So, and that is very common practice, is done by any chip provider like Intel, or say other companies, which actually run the whole processor in a FPGA board, right. So, there where the multiple FPGA stack and stacked together, maybe 10, 15, 16, 80 FPGA board are stacked together, and the whole processor, there may be million line of Verilog code, that the whole processor circuit is synthesized into the FPGA board, right. And then that is become your processor. Now, you install operating systems, say Windows, Linux on this top of this, and you execute, you play, you write program, you execute some, you browse internet, you do whatever that your computer can does, right. So, that is something called prototyping, that you before the actual fabrication of the big circuit, you dump that the whole thing in FPGA and you run it for some time, just to see if it is creating some problem or not, right. So, that is just give you some confidence that the circuit that we are going to fabricate has no issues, right. That is called ASIC prototyping. And now, you think about a circuit of that scale, and it has lot of gating or something, and you just try to do it in FPGA, then this clock gating will create a serious problem, right. You cannot map all those clocks to that to the FPGA board. So, then this FPGA synthesis tool try to do what is the most thing it try to do is that it try to do the gated clock removal. It try to remove this gated clock from your circuit, so that that particular whole design can be synthesizable for RTL, because you cannot do, at this point you cannot remove the gated clock from your actual circuit, then the whole purpose is lost, right. So, that is something does by this FPGA synthesis tool like Simplify Pro, Premiere from Synopsys, or Xilinx, or Altera synthesis tool, right. And it is not necessary requirement for the FPGA module that all low power optimization of ASIC will be made by the FPGA synthesis, because the primary objective is to check the functionality, not but the low power requirement things cannot be verified using FPGA, right. So, the kind of strategy you should take about that here is that problem that one clock may go to multiple hierarchies through multiple hierarchies, multiple layer, and that will create a serious problem for the FPGA prototype. I just already explained that. So, the strategy you should take about that when you design your this ASIC circuit, you should create a clock module. It is a good design practice that you keep your all clock in a single module, whatever the, so you create a 3 clock domains here, 4 another 3 here. So, there are 6 clock domains, but you create all this module everything in a one module. So, that this is something whenever the FPGA synthesis is happening, it is easy to detect all your clock domain easily and can be processed easily, right. So, this is kind of a good design practice that you should follow when you are actually thinking about your having a ASIC prototyping of your design, FPGA prototyping of your designing, right. The second thing that synthesis tool, the FPGA synthesis tool does is a gated clock conversion. It does the reverse of that. It does the reverse of gated clock. So, whenever there is a clock which is gated with several enable signal, it may be one enable or multiple enables, and there is a big combination logic, and that become your clock. It just do the reverse. It just remove out this all this enable and put them at the enable of the clock, and clock is coming directly to this. I mean, this is just the reverse of clock gating, right. So, you just put enable to the enable signal, all the enable logic to the enable signals, right. This is what is called gated clock conversion, and that is related to the FPGA. So, here is an example. Suppose you have this circuit here where you have a gated clock and this is clock and enable. If you just synthesis this with the simplify pro of synthesis of synopsis, and if you enable the GCC gated clock conversion thing enable, what will happen here? It will actually move this remove this AND gate, it take this enable and it will connect directly this enable to the enable point, and this clock directly to the clock point of this particular flip flop, right. Similarly, if you have bigger logic here, you can see here there is enable 1 here, enable 2, and there are a lot of logics here, and this is basically gated clock, right. This is the gated clock. It is actually able to detect this circuit and remove everything, optimize this, and effectively put this enable 1. This circuit effectively means OR of enable 1 and enable 2. So, it do the optimizations and put this as the enable, and clock is directly fed into the registers, right. This is what this tool automatically does that. This is called automated gated clock conversion for ASIC prototyping. Okay. And I talked about this integrated gated clock also, where I use a latch as well as the AND gate, and if you just do through this synthesis tool, what will happen again, you just remove this AND gate and this latch, and again this enable will be directly connected to the enable point, and this clock directly to the clock point. This is what is will happen in synthesis, real synthesis, right. This is real synthesis result. I just give a capture one of this register. This is a 5 bit register. This is the 5 points, right. So, there are 5 bits, and this is just one sample of that. Right. This is what the synthesis tool does, just to remove the gated clock things, right. So, in summary, today we have discussed about this several optimization technique or transformation technique that are related to power. We have discussed about clock gating, we discussed about this lowering the voltage of your design, we discussed about this dual edge triggered flip flops for lowering frequencies, we discussed about different kind of RTL transformation, just like this changing the multiplexer architecture, or this removing some glitchy control signals, or connected clock to that glitchy controls, and integrated clock techniques. Those are techniques that are improving the power consumption of your circuit. We have also discussed the clock domains, issues with the clock domain, clock skew problem, and then we talked about this metastability because of that clock domain crossings, and we talked about 3 specific techniques like phase control, double flopping control, and FIFO control issue and solution to avoid this metastability of this clock domain crossing problem, right. And then we talked about this, what is the problem with clock gating when you are doing ASIC prototyping in FPGA, and how it is actually avoided using gated clock conversion. With this, I will complete this particular module. Thank you.